Lewis structure modeling is a useful tool for helping scientists understand how atoms bond together. And while Lewis structures are helpful in understanding the basics of ionic bonding, this video is going to focus primarily on covalent bonding, as Lewis structures tend to show the complexities of covalent bonding much more effectively. Lewis structures are essentially simplified Bohr models. We use the elemental symbol, so for lithium Li, to represent the nucleus of the atom as well as the core electrons or non-valence electrons. Then we use a series of dots surrounding the atom to represent the valence electrons. In the case of lithium, which only has one valence electron, we put a singular dot around it. Beryllium, which has two valence electrons, would be given two dots. Now, there's no technical way, no technical rule about how you're supposed to arrange the dots. You tend to arrange them based on what's going to be the most beneficial for your Lewis structure. So beryllium could be drawn with the two dots on one side like this. We can also put one on each side. Sometimes that's more beneficial. Sometimes we might want to do one on one side, one on the top, one on the bottom. But the key thing is that there should be two electrons represented. Carbon has four valence electrons, and so again, we could arrange these. We could put two on one side, two on another side. Usually with carbon, we tend to just do one on each of the four sides of it. But again, it varies. Oxygen with six valence electrons typically look something like this, and et cetera, et cetera, et cetera. These Lewis structures can be very helpful because when we draw models of covalently bonded molecules, we can use these Lewis structures to show how the electrons have moved around in order to facilitate that bonding. When it comes to chemical bonding for molecules for these covalent structures, there's two major types that we talk about. One of them is octet structures, and the other one are octet breaking structures. This refers to the octet rule. The octet rule is the tendency of atoms to have 8 valence electrons when they chemically bond. There are some exceptions to this. For example, hydrogen, due to the fact that it only has the first energy level, which can only hold 2 electrons, will never have 8 valence electrons, but only go up to 2. But most elements on the periodic table, usually when they engage in covalent bonding, as well as ionic bonding, they typically try to achieve having access to 8 valence electrons, whether that's through giving and taking or sharing electrons. We'll start off by talking about structures that obey the octet rule, since these tend to be the simplest to start with. Let's start off with 3 diatomic molecules, F2, O2, and N2. We start by drawing the Lewis structures of the fluorine atoms. Fluorine has 7 valence electrons, so each of the fluorines will have 3 pairs of electrons plus a lone electron. Since each fluorine already has those 7 valence electrons, each one only needs 1 additional electron in order to meet the octet rule. The easiest way to accomplish this is by taking the lone electron that each one has and merging them together into a shared orbital. They currently each have their own orbital for those lone electrons, but when we bond together, we overlap their orbitals and create a new orbital that contains both electrons in it. This sharing of these 2 electrons is what's referred to as a covalent bond. We represent this covalent bond with a line between the 2 fluorines. That line represents those 2 electrons that are now shared in the same orbital between the 2. This is how we establish a covalent bond. Now let's try the same thing for oxygen. In the O2 molecule, each of the oxygens only has 6 valence electrons as opposed to fluorine's 7. This means each oxygen is going to need 2 additional electrons in order to meet the octet rule. So unlike fluorine, which only had to share once, because oxygen needs 2 additional electrons, we're going to have to share twice. So each oxygen will contribute 1 electron to 2 different bonds. And once again, we can represent each of the shared pairs of electrons as a line between the oxygens. In this case, there's going to be 2 lines, so this is a double bond. When we look at the N2 molecule has, each of the nitrogens has 5 valence electrons. This means nitrogen is going to have to share 3 times in order to reach the additional 3 electrons that they each need in order to meet the octet rule. And once again, we can replace those shared pairs of electrons with a line each, so that gives us 3 lines, and this is a triple bond. Now let's try this with some more complex molecules. So we'll use CO2, HCN, and SO2. Now when we deal with three or more atoms consisting of more than one element, one of the things we run into is we have to figure out how we're going to arrange these atoms. Because, for instance, taking the CO2 molecule, we could go O to C to O, we could go C to O to O, and so this creates a little bit of a complication for this. The general rule with this is that because we write chemical formulas by increasing electronegativity values, the first element written usually is the lower electronegativity, which means that it's more willing to share electrons. Since it's more willing to share electrons, it's more favorable to put that atom in the center of the molecule. So in the case of CO2, we're actually going to put carbon in the center between the two oxygens. Once again, we'll arrange the valence electrons around each of their symbols, carbon having 4 valence electrons and each oxygen having 6. Since each oxygen wants 2 additional electrons and carbon wants 4 additional electrons, this makes the sharing very easy because we just have to share we have to share 2 pairs of electrons between the carbon and each of the oxygens. This will give us 2 double bonds, one between the carbon and each of the oxygens. And then, of course, we can go around and count the number of valence electrons that each atom has to make sure that they're all meeting the octet rule. Each oxygen has 4 electrons to itself in 2 pairs, and then has the 2 bonded pairs of electrons, so you get a total of 8 between that. And then the carbon has 4 pairs of bonded electrons, giving it a total of 8 as well. Now, when we look at HCN, because of our previous rule we talked about with putting the first atom written in the formula in the center, we would be tempted to put hydrogen in the center of this molecule with carbon on one side and nitrogen on the other side. The problem with this is that since hydrogen only wants to have 2 valence electrons because it only uses that first energy level, well, if you only have 2 valence electrons, you can only form one single bond. And one single bond is only enough to bond to 1 additional atom. Being in the center requires you to bond to at least 2 additional atoms, and therefore hydrogen can never go in the center of a molecule. So in this case, we're going to have to go to the next one, which is carbon, and throw carbon in the center. Now that we have the structure in order, we can go about and put the valence electrons around each of the atoms. So hydrogen gets 1, carbon gets 4, nitrogen gets 5. Since hydrogen only wants 1 additional electron, it's only going to share once, and therefore we will share these electrons between the hydrogen and the carbon. Carbon still needs to share 3 additional electrons in order to get to its total of 8. Nitrogen needs to share 3 electrons in order to get to its total of 8. So we can go through and share these last remaining electrons here, leaving nitrogen with a lone pair of electrons to itself. This will give us a single bond between the hydrogen and the carbon, and then a triple bond between the carbon and the nitrogen. When we look at sulfur dioxide, again, because we don't have hydrogen as an issue here, once again we can go back to our rule about having the first element listed in the center. So in this case, we're going to put sulfur in the center with the oxygens on both sides, very similar to what we saw with CO2. Once again, we'll place our valence electrons. In this case, all atoms are going to have 6 valence electrons, since sulfur and oxygen are in the same column. From here, we can start sharing electrons to meet the octet rule. So what we'll do is we'll start on one side. We'll start with the leftmost oxygen and the sulfur. Again, we know that oxygen needs 2 additional electrons in order to meet the octet rule, so we'll start by taking 2 electrons and sharing them from the oxygen to the sulfur. So now oxygen, on that leftmost oxygen, has 8 electrons. It has the 4 lone electrons as well as 4 bonded electrons. The problem we run into now, however, is that sulfur also has all 8 electrons at the moment. It also has 4 lone electrons and 4 bonded electrons. That means that the oxygen on the other side is left with nothing to bond with, if we're going to do equal sharing. So what's going to happen here is that because, again, that sulfur is a lower electronegativity, oxygen can kind of bully sulfur into giving up electrons that it doesn't necessarily need to or want to give up. So what the oxygen can do instead is essentially force sulfur to share both of the electrons and create a covalent bond between them, where that oxygen on the right is giving up absolutely nothing for this. This will create a double bond between the sulfur and one of the oxygens and a single bond between the sulfur and the other oxygen. Because in that single bond between the sulfur and the oxygen, the sulfur gave up both the electrons. There's not an equal sharing thing going on here. It's just one atom giving up both electrons. This is what we refer to as a coordinate covalent bond. Coordinate covalent bonds are where one atom contributes both electrons to a bond, and the other atom does not contribute electrons to that particular bond. Now, sulfur dioxide also presents another problem because since oxygens are absolutely identical to each other, there's nothing different about the two of them, there's no reason why one oxygen would get more preferential treatment than the other oxygen in a molecule. So the fact that one oxygen is double bonded, which is more ideal for it, and the other oxygen is single bonded, which is less ideal, doesn't really make sense. And this is always the problem with models. Models are flawed. When we look at sulfur dioxide, the Lewis dot structure shows us a double bond and a single bond. But electron motion is much more fluid than that. And so what we actually have to do as far as Lewis structures is look at it in terms of what are called resonance structures, where resonance structures show the movement of these electrons in different positions relative to each other. With Lewis structures, we can show this resonance by drawing the same molecule, SO2, in two different ways, where the double bond is on the left side and the single bond is on the right side, and then as an alternate version, the single bond is on the left side and the double bond is on the right side. Now, the reality is that these Lewis structures don't actually show the fluidity of that electron motion, and the proper way to interpret a resonance structure system like this is that it's not really either of these structures, but it's really a hybrid of these two structures together, where that extra pair of electrons, that second pair of electrons in the double bond, is actually spread across both atoms, or across all three atoms. So it's creating this distribution of those electrons in a way that we can't really represent effectively using Lewis dot structures. As a result, we don't really think of SO2 as having a double bond and a single bond, because we kind of average these bonds together and create and look at it in terms of more of like a 1.5 bond. It's an order of 1.5. Like a single bond is a first order, a double bond is a second order. So because of these resonance structures, this movement of electrons, SO2 really has two bonds that's not a first order and a second order, but two 1.5 order bonds. Another way to build Lewis structures that can be a little bit more helpful with dealing with these coordinate covalent bond situations is one where we take all the electrons away from the molecule and then put them back wherever they're needed. So we'll use SO2 as an example again for this. We start by getting our basic arrangement of the atoms, again sulfur in the center with the oxygens on either side. And then we count up the total number of valence electrons that we have to work with in this model. In this case, because sulfur has 6 valence electrons and each oxygen also has 6 valence electrons, this will give us a total of 18 electrons. Our first requirement is to make sure that all the atoms are bonded to each other. And the simplest way to do this is with a single bond between each of the atoms. So we just draw in a single bond between the sulfur and each of the oxygens. Because we've now used up 4 electrons for this, this will bring our total number of electrons that we have available down to 14. Now we can start placing the remaining electrons around to try to meet the octet rule. So usually the best thing to do is start with the outside atoms and then work towards the center, and I'll show you why in a second. So we'll start with the left side oxygen. This oxygen right now has 2 electrons covalently bonding it to the sulfur. That means it has 2, and we need 6 additional electrons. So we're going to take 6 of those 14 remaining electrons and put those as lone electrons on the oxygen. This will bring our total down to 8. Now we'll go to the oxygen on the right-hand side and do the same thing. Because it just has that single covalent bond, it's going to also need an additional 6 valence electrons. And so we will take those and just place them around the oxygen. Because we used another 6 of our valence electrons, that's going to take us from 8 down to 2. Now, since both the oxygens have their 8 electrons, we'll go to the sulfur. So with sulfur, we're going to go and put electrons in here. Now, sulfur currently has 4 electrons from the 2 bonds, so sulfur wants 4 more. The problem is that right now we only have 2 additional valence electrons that we can place. So we're going to start by placing those 2 electrons. This will now bring us down to 0 available electrons remaining. Since sulfur is still missing a pair of electrons, but we have no more valence electrons to place, what we're going to do to handle this deficiency is do a little bit of redistribution. So now what we can do is we can take one of these pairs of electrons that one of the oxygen has, and instead of letting oxygen have that to itself, we're going to share them between the sulfur and the oxygen. By creating this double bond, we've now allowed sulfur to get its 8 valence electrons without taking any away from oxygen, just redistributing them by sharing them. So this is just a different way of creating Lewis structures. There's the method where you can draw each atom's Lewis structures as is and then start moving electrons and sharing that way. I tend to find this method works really well because yes, we're taking all those valence electrons away and putting them wherever we want them to go, but in the end, as long as we're obeying the rules about creating these covalent Lewis structures, the electrons will end up where they're supposed to go in the first place. And this usually gets around the whole coordinate covalent bond issue about like when do we have to have one electron giving up 2 electrons to the bond and things like that. Now let's talk about structures that break the octet rule. There are 2 types of molecules in this category. There are suboctet and there are expanded octets. We'll start off by talking about suboctets. These are pretty straightforward. A suboctet is a situation where an atom receives less than a full valence shell of electrons. We don't often consider hydrogen as one of these because even though hydrogen doesn't get 8 valence electrons, the octet, it does fill its valence shell because its valence shell only holds 2 electrons. This is more common with, primarily it happens with the elements beryllium and boron. And that's because beryllium only has 2 valence electrons and boron only has 3 valence electrons, which makes it very tough for them to acquire the extra electrons they need in order to meet their octets. So let's look at a case like boron trihydride. In BF3, we're going to put boron in the center because it is the less electronegative element with the 3 fluorines surrounding the boron. In this case, it's easiest just to assign the valence electrons to their original atoms. So we'll start by putting 7 valence electrons around each of the fluorines and 3 around the boron. So the next thing for us to do is to share the electrons between the boron and the fluorine to meet octets. We'll start with the fluorines, where each fluorine has 7 valence electrons, so they only really need to share 1 additional time in order to meet their octet. So we'll share once between each of the fluorines and the boron. And what this is going to do is it's going to give us 3 single bonds. Now at this point, all the fluorines have their 8 valence electrons, but boron only has 6 because of the 3 single bonds. When we were looking at the coordinate covalent bond situation with sulfur dioxide, we said, well, we could just have one atom give up an extra pair of electrons in order to make this work out. The problem is that fluorine is a very, very electronegative element, and boron is a very low electronegative element. So boron is okay with sharing, but fluorine hates to share. So getting fluorine to give up a pair of electrons to boron for no reason is not something it wants to do. Therefore, boron gets stuck with only having 6 valence electrons in this structure, which is why it has a suboctet. So now let's look at expanded octets. Expanded octets are where one atom has more than the 8 valence electrons that we typically expect under the octet rule. To help understand expanded octets better, we're first going to look at a method of analyzing molecules called formal charge. Formal charge is it's a charge value that we give to each of the atoms in a molecule, based on the idea that the electrons in a covalent bond are being shared equally. This is ignoring the polarity of bonds, so it's not totally realistic, but it does help us in understanding when we can break the octet rule and when we can't. The way we calculate formal charge is to start by taking the total number of valence electrons that the atom has in its neutral state when it's not bonded. Then from that, we subtract the number of non-bonded electrons in the molecule for that atom. Then we subtract half the number of the bonded electrons attached to that atom. Let's use sulfur dioxide as an example. From previously, the Lewis structure for sulfur dioxide is this. Let's start by figuring out the formal charge of this oxygen. All oxygens start off with 6 valence electrons before bonding. Then from that, we're going to subtract the 4 non-bonding electrons that we see in the Lewis structure. And then we're going to subtract half the number of bonded electrons. There are 2 bonds, so that's 4 bonded electrons. So we'll subtract half of 4, so 2 additional electrons. This will give this oxygen a formal charge of 0, which is what we expect because the oxygen is bonded exactly the way it normally wants to. It's bonded twice in order to get its 2 additional electrons. Next, let's look at the sulfur. Sulfur also starts with 6 valence electrons. In this diagram, we're going to subtract from that 2 non-bonding electrons for those 2 dots that we see on the sulfur, and then we'll subtract half of the 6 bonded electrons from those 3 bonds. This will give sulfur a formal charge of +1. This is expected because sulfur is bonding 1 additional time beyond what it usually wants to bond. Since sulfur normally needs 2 more electrons, it'll usually bond twice. In this case, we're forcing it to bond 3 times. Finally, we'll look at the remaining oxygen on the right-hand side. Oxygen once again starts with 6 valence electrons before bonding. Now in this model, unlike the other oxygen, this oxygen has 6 non-bonding electrons to itself that we'll subtract from the original 6 valence electrons. Then from that, we'll also subtract 1/2 of the 2 bonded electrons from that single bond between the sulfur and the oxygen. This will give this oxygen a formal charge of -1. Again, this is expected because this oxygen bonded 1 fewer times than it normally would bond. Oxygen usually will bond twice. In this case, it only bonded once, meaning it had an extra pair of electrons to itself, giving it a more negative charge than normal. Notice that when you add up the formal charges of the molecule, they add up to 0. This is also appropriate because the overall molecule has a 0 charge to it, and therefore all the formal charges should add together to equal that same charge. When we look at things like polyatomic ions, which have non-zero charges, the formal charges should add up to that non-zero value as well. So how does this apply to expanded octet structures? Well, the thing is that the reason we use formal charges is because the closer to 0 a formal charge gets, the more stable the molecule is. We're trying to get these atoms to have these 0 formal charges. It means they're sharing the appropriate number of times. So usually what we're trying to do is bring these formal charges down to 0 if we can. If we can't have 0 as a formal charge, then we try to make sure that the more electronegative elements end up with the negative charges and the less electronegative elements end up with positive charges, if that's what has to happen. Let's take a look at an alternative version of sulfur dioxide where we can remedy the situation. In the case of this model, this is a little different. In this case, we have sulfur breaking the octet rule, because it actually has 10 electrons. It has 8 bonded electrons and then those 2 lone pair electrons. The oxygens are identical in that both have a double bond. Now, if we do the formal charge assessment for this, let's start by looking at the oxygens. Both oxygens are the same, so we can cover both of them together. Each oxygen once again starts with 6 valence electrons before bonding. Then we're going to subtract those 4 non-bonding electrons and then 1/2 of the 4 bonded electrons, giving us a formal charge of 0. Now let's look at our sulfur that's breaking the octet rule. The sulfur, again, starts with 6 valence electrons before bonding. Then we're going to subtract those 2 non-bonded electrons that it has, and then we'll subtract 1/2 of the 8 bonded electrons. This is also going to give us a formal charge of 0. By having sulfur break the octet rule, we were able to stabilize the molecule and reduce those formal charges to 0. So under the octet rule, you would see that former structure, but when we look at formal charges and deal with expanded octets, then we see elements like sulfur breaking the octet rule. One important thing to note is that in order to break the octet rule, you need a significantly large valence shell. And this can only be accomplished when you're talking about a valence shell that's either the 3rd energy level or higher. This means that elements that are on the 2nd row of the periodic table, so boron, carbon, nitrogen, oxygen, fluorine, cannot break the octet rule. Those ones are stuck dealing with the octet rule and have to deal with the formal charges as appropriate. Any of the elements below that, however, those nonmetals below that, so when you're talking about like phosphorus and sulfur and chlorine and iodine, these elements can break the octet rule in order to reduce those formal charges to 0.